Look at us. I mean, look at us. Who would have thought? Well, who cares? We're back. It's been a while. This was supposed to be like a few weeks ago. I was looking forward to do this one, but a lot of things happened. So we have no choice but to postpone it for a bit, but I'm not disappearing just yet. We're still here and it's still the great teacher. Yes, I have to say that for the sake of our sanity. Here right back for three lessons. So it's gonna be a long one again. So please forgive me. We're gonna talk about remainder theorem, factor theorem, and of course, rational root theorem. You know what? Let's just jump right into it. Let's kick things off with the remainder theorem. So these theorems that we'll be discussing for this one will focus on polynomials, equations, and functions. So starting off with the remainder theorem, our target for this one is to state the theorem and at the same time, of course, from the name itself, to find the remainder of a given polynomial. So for example, let's say that we're being asked to find the remainder of 5x squared minus 4x plus 3 when we divide it by x minus 3. So from the previous lessons that we've had, we have learned to use syntactic division for this one. So using syntactic, what we can do is first maximize the divisor, which is x minus 3. So in this case, in order for us to continue with the process of syntactic division, we have to identify the syntactic divisor. So let us equate x minus 3, our divisor, to 0. And then we have to transpose negative 3 to the other side or add 3 to both sides to get the value of x being positive 3. Hence, x is equal to 3. This will be our syntactic divisor. So we will have 3. And then we have 5x squared minus 4x plus 3. So therefore we have 5, negative 4, and then 3. So continuing with syntactic division, we bring down 5. 5 times 3 is 15. Negative 4 plus 15 is 11. 11 times 3 is 33. 3 plus 33 is 36. So here, if we translate the meaning of 5, 11, and 36, we'll be able to say that we have 5x plus 11 plus 36 all over x minus 3, since our remainder is 36. So you have to take note of that. So just an introduction on how the remainder theorem works. We're now going to introduce a function notation. Let's say that we have the function f of 3 and we have 5x squared minus 4x plus 3. This came from f of x, baliktad, f of x equal to 5x squared minus 4x plus 3. And let's say we have f of 3. So the meaning of that is we're going to change the value of x to 3. So to continue with this one, we're now going to have 5 times 3 raised to 2 minus 4 times 3 plus 3. So what we're going to have here is 45 minus 12 plus 3. So this is going to give us 45 minus 12 is 33 plus 3, 36. So now here's what I want you guys to observe. When we did f of 3, we got 36 as our answer. And this one right here is actually the remainder. And what you're seeing on the right side of your screen is our remainder theorem solution, the application of remainder theorem. So as you can notice again, using syntactic division, we have 36 as the remainder, and using the remainder theorem, we have 36 as the remainder. So how does the remainder theorem work? So what I'm going to show you here first is the application of the concept and the derivation of the formula. So let's say that f of x is a linear polynomial where, f of x is a polynomial divided by the linear polynomial x minus c. So the x minus c is like a binomial divisor that we maximized earlier in the earlier example. I'm so sorry if my English is stuttering. It's 12 a.m. My goodness. Anyway, so we have the polynomial f of x divided by a linear polynomial x minus c. and it's equal to the quotient plus the remainder or divisor. So in here, what you're seeing on the next step is wherein we multiplied both sides by x minus c. That's why there's no longer a divided by x minus c on the left side. And then we have here, what if we just have the constant r, for example, standing for the remainder. And if we continue with this one, this is actually the remainder theorem. How does that work? Let's make x equal to c. So you change your x's to c. C minus c, that is 0. 0 times q of c, that will give you 0. So all that's left is r. So it looks confusing, and I understand that because it's more of like a derivation of the formula. But all it needs to say or wants to say is that we have a polynomial and it's always equal to its remainder when we substitute x being equal to c. So we will get this one right here from the divisor, the x is equal to c part. Now, to make this much more clear, let's say that we have the following examples. Let's start with the first one. We have x raised to 3 minus 2x squared plus x plus 3 divided by x minus 1. Our divisor is x minus 1, so we equate this to 0, transpose negative 1 to the other side. Our x is equal to 1. Hence, our function will be f of 1 equal to x raised to 3 minus 2x squared plus x plus 3. So what we will do here again is change our x's to 1. Okay, so we will have 1 raised to 3 minus 2 times 1 raised to 2 plus 1 plus 3. Now, it's important again that we can only do the remainder theorem after we find the value of x. Okay? You have to remember that. Next, we'll have 1 minus 2 plus 1 plus 3. So we will have here the remainder of f of 1 being 3. So this is your remainder. 3 is the remainder for this example. Continuing, now let's have the one on the right side. We have x plus 1 this time. So let's equate that to 0. Your x will be equal to negative 1. So you will have f of negative 1 and our given polynomial 4x raised to 3 plus 3x squared minus 16x minus 13. Now, as you can observe from the left side, I have put the substitution inside a parenthesis. That's really important, especially when it comes to negative numbers. So we'll have 4 times negative 1 raised to 3 plus 3 times negative 1 raised to 2 minus 16 times negative 1 minus 13. Now, this is our f of negative 1. Now, the importance of the parenthesis in there is so that the negative sign is included when we raise it to an exponent. So we'll have here 4 times negative 1 raised to 3 is negative 1 plus 3 times negative 1 raised to 2, that's positive 1. Negative 16 times negative 1, that's positive 16 minus 13. So we're going to have negative 4 plus 3 plus 3. So the answer here is positive 2 for f of negative 1. So this right here is our remainder. So that's how the remainder theorem works, as easy as that. Basically, it's similar to the process of synthetic division, but all we have to do is to find the value of x, our synthetic divisor in the previous concept, and then substitute that to the entire polynomial function given. So let's try one more, I think. Yes, we still have one more here. So identify the remainder of the following. So we have x plus 2 this time around. So therefore, what we're going to have is x plus 2. Equate that to 0. Transpose positive 2. X is equal to negative 2. Now we will substitute negative 2 to our given function. So we're going to have f of negative 2 equal to, now, so we can save some time since we have already shown some complete solution earlier. We can actually directly substitute here. So we can have 2 times negative 2 raised to 4 minus 4 times negative 2 raised to 3 minus 7 times negative 2 raised to 2 minus 13 times negative 2 minus 10. Now we'll have here 2 times, 2 times 2, 4 times 2, 8, 16. So 2 times 16, we have here negative 4 times negative 8. We have here negative 7 times 4. We have here 26 minus 10. Continuing, we'll have 32 plus 32. Yep, that's correct. 32 plus 32 minus 28. 26 minus 10, that's 16. So this is 64. 64 minus 12, we'll have 52. Yep, I think it's 52. Am I correct? It's 52 the remainder. 64 plus 16, that's going to be 82. Wait, what? Wait, I'm lagging now. Yeah, it's 52. Negative 28 plus 16, that's going to give us negative 12. So 20, okay, that's the remainder. So 52 is our remainder for f of negative 2. So now that we have done these kinds of examples, now let's try what if we have a given where there is a missing value other than x. So it says here, find the value of k if 5x raised to 5 plus 3kx cubed minus 6kx squared plus 9 has a remainder of 23 when divided by x minus 1. Earlier, it was mentioned in the remainder theorem. It stated there earlier that, now my handwriting is so horrible, that f of c is equal to the remainder, or r, right? So that's what was explained earlier. So now what does it imply with these kinds of examples? So let's not panic here. It's simple. Let's go back to our x minus 1. Let's equate it to 0. Transpose negative 1, add 1 to both sides, or whatever method you wish to use. We'll still get x equal to 1. Okay? So now what we will do first is work on the function. Let's say we have f of 1 equal to 5 times 1 raised to 5 plus, be mindful here, 3k times 1 raised to 3 minus 6k 1 raised to 2 plus 9. Next, we have here 5 times 1 raised to 5, that's just 5, plus 3k, because 1 raised to 3 is 1, minus 6k plus 9. This is f of 1, right? Observe this one. So f of 1. Next, let's combine like terms. We have 5 and we have 9. That's going to be equal to 14, positive 14. But also we have 3k and negative 6k, right? So that's going to be equal to negative 3k. So now you're wondering, what do we do now? Let's go back to the remainder theorem. F of c is equal to the remainder. Our f of c here is our f of 1. And the remainder is actually given, which is 23. So what we will do now is we will change f of 1 into our remainder being 23. That's the magic here. Our f of 1 will be 23 based off of the formula or the concept of the remainder theorem. So this will still be equal to negative 3k plus 14. So now what we'll do is we isolate the variable, transpose 14 to the other side. We have 23 minus 14 is equal to negative 3k. 23 minus 14, that's going to give us 9 is equal to negative 3k. Am I correct? Yep. So if you continue with this solution, we're going to have 9 is equal to negative 3k. Divide both sides by negative 3. Therefore, our value for k is none other than negative 3. So that's the answer. So the value of k is negative 3, so we can substitute that to have our polynomial. So we can do that right here. So let's just divide this a little. So our given is 5x raised to 5 plus 3kx cubed minus 6kx squared plus 9. We change our k to negative 3. We're going to have 5x raised to 5 plus 3 times negative 3 x cubed minus 6 times negative 3x squared plus 9. So our actual polynomial is 5x raised to 5 minus 9x cubed plus 18x squared plus 9. So now there's no k left. So that's how it works. So you don't have to panic. Just continue with the remainder theorem, and always remember that the function is always equal to its remainder once we have substituted the value of the constant or the synthetic divisor. So without further ado, let's go to the next one. And that's why you don't have to worry. Once you understood the concept of remainder theorem, factor theorem is easy peasy. So if you find the previous concept difficult or confusing, I hope factor theorem clarifies it for you. So it's the same concept. We're going to state the theorem and at the same time identify if the given divisor is a factor. So how does it work? Basically, since we have explained the derivation of the formula, you don't have to worry about that. But this time around, there's an emphasis. It's no longer equal to the remainder. It's now equal to 0. Why is that? Because the goal now is to get a remainder equal to 0. Because when the remainder is 0, it implies that a certain given is a factor. For example, right, if you divide a number like 10 by 2, the answer is 5. There's no remainder. So that means 5 and 2, that's correct. 5 and 2 are factors of 10. So that's how it works. So to make this simple, let's apply the factor theorem for this given example. Same case with remainder theorem. We go with our given, x minus 3, equated to 0, transpose negative 3, our x is equal to 3. Now that we have identified that, we can work on our function where our x is 3, and we substitute that to our given. Doing so, we're now going to have 3 raised to 2 minus 5 times 3 plus 6. So this will be 9 minus 15 plus 6. And this is equal to 0. So f of 3 is equal to 0. So the meaning of this is that the remainder is 0 and x minus 3 is a factor of the given polynomial. So that's how the factor theorem works. As simple as that. So let's continue with some more examples. You can work on this one. So this one is a bit long, but same process. We now have x plus 2. So again, let's have our x plus 2 equated to 0, transpose to positive 2. We're going to have x is equal to negative 2. Now, since it's written already, the function here, let's say p of negative 2. Now, for those who are wondering, the functions can have different names. It could be p of x, q of x, a of x. It doesn't matter. The functions can have different names. That's why here you don't have to worry. Just follow the process. Trust it. You have 3 times negative 2 raised to 4 plus 5 times negative 2 raised to 3 minus negative 2 raised to 2 plus negative 2 minus 2. Again, suggestion, always make sure to put them inside the parentheses. This will be 3 times negative 2 raised to 4 is 16 plus 5 times negative 2 raised to 3 is negative 8 minus negative 2 raised to 2 is positive 4. Then plus negative 2, that means negative 2 minus 2. Continuing, we'll have 48. 5 times negative 8, negative 40. Negative 4 minus 2 is negative 8. Where did we get negative 8? Negative 4, negative 2, negative 2. Negative 4 minus 2 is negative 8. And if you continue with this one, 48 minus 40 minus 8 is 0. So our p of negative 2 is 0. Hence, x plus 2 is a factor. As simple as that. Don't overthink it. Just go with the divisor first. Isolate x. Use the value as something that you will substitute to the given function and see if the answer is 0. And speaking of that, let's now determine if x plus 1 is a factor of the following polynomials. Now, I expect that at this point, you know already how to isolate the variable. So we know here that we're going to have x is equal to -1 for both examples. Our goal is to identify which of the following polynomials has x plus 1 as a factor. So we now substitute x is equal to -1. So let's say f of -1 equal to 3 times -1 raised to 4 plus -1 raised to 3 minus -1 raised to 2 plus 3 times -1 plus 2. So this will be 3 times 1 plus -1 minus 1 plus -3 plus 2. This will be 3 minus 1 minus 1 minus 3 plus 2. So if we continue with this one, this will actually give you 0. 3 minus 1 minus 1 minus 3. Am I correct with that? Yep. So this means that x plus 1 is a factor of the given. So how about the one on the right? So we will have f of -1 here. Let's have -1 raised to 6 plus 2 times -1 times -1 minus 1 minus 4. So if you continue this one, f of -1 is equal to 1 plus -2 times -2 minus 4. So our f of -1 is 1 plus 4 minus 4. This is 1. 4 minus 4. So there is a remainder. Hence, x plus 1 is not a factor of the given polynomial. So that's what I want you to remember with this example. So as easy as that, there's nothing to really worry about. Okay? So let's go with our last example, similar to remainder theorem. Let's say we have k. Now, as you can see here, it's f of d. Again, it don't matter. Your d here is like the x earlier. So there's nothing to worry about. So let's start with d plus 9. Equate it to 0. Transpose d is equal to -9. So now we're identifying if it is indeed a factor. So that means all we have to do is to change f of d to 0. So later on, f of d should be equal to 0. So let's continue with this one. So f of -9 is equal to -9 raised to 3 plus k times -9 raised to 2 plus 3 times -9 minus 54. So if you continue with this, 9 times 9, 81 times 9, 729. -729 plus -9 raised to 2, positive 81k. 3 times -9, -27 minus 54. And again, so that this will be quick, we want our f of d to become 0. Since this is our f of d, this will now become 0. So to continue with this, let us first simplify. Keep our 0 here. -729 minus 27 minus 54. What will be the answer here? This will be -810 plus 81k. Yep. Then we transpose -810 here. This will be positive 810 equal to 81k. Divide both sides by 81. Then our value for k is none other than 10. So that's it. So if you want to know the actual polynomial, substitute 10 to k. So we're going to have d raised to 3 plus 10 d squared plus 3d minus 54. That's it. So we just change our k to 10. So that's how it works. That is the factor theorem. And I guess so that we're not going to spend more time, you may pause this one, if you're feeling restless already. You can pause this one. But as for me, we won't stop because we don't know how to stop. And nobody can stop us because they ain't us, right? So now we're going with rational root theorem. So rational root theorem is actually a bit long because it's the application of all the concepts we discussed so far about polynomials. From synthetic division, long division, you may apply that if you want to. It's a longer version. I wouldn't want to do that, but you can apply those things. the same time the remainder and factor theorem. Because the goal here in rational root theorem is to identify the rational roots. So at first, of course, we have to state it, and then after that, we're going to generate a list of factors of a constant, and then find the roots. That's it. So what are the factors of 36, for example? Now, what you're seeing on your screen is a grade 7 concept, and as you can notice, we're now using the concept of plus minus. Now, what does it imply? It implies that we're considering both the positive and the negative factors, because 36 is a whole number that is a positive number, right? We know that 6 times 6 is 36. But at the same time, negative 6 times negative 6 is also positive 36. Similar with negative 1 times negative 36. So it's still a factor of 36. Those are the things that we have to remember now that we are working on the rational root theorem. So at the same time, as I've said earlier, we can apply a lot of concepts. Now, I'm not going to show you using quadratic formula because it's a bit long. The space is not going to be possible, but I'll explain this. If you know how to use the quadratic formula, you may use that instead of factoring, because some kids don't like factoring, but it's your choice. So now, let's work on identifying or working on the rational root theorem. So we're going to work on a blank example later, but basically, we have the polynomial. We identify the constant being negative 6, and then we identify the leading coefficient. Guys, the meaning of leading coefficient is the coefficient, numerical coefficient of the variable of the highest degree in the given polynomial. So as you can notice, we identify their factors. For negative 6, we have positive negative 1, positive negative 2, positive negative 3, and positive negative 6. For 4, we have positive negative 1, positive negative 2, and positive negative 4. So now, how does the rational root theorem work? Simple. As you can see on the table in front of you, there is a reason why the constant factors are on top while the factors of the leading coefficient is at the bottom. Because the concept of possible rational roots for the rational root theorem is as simple as dividing each factor of the constant by each of the factors of the leading coefficient. So for example, we can have 1 divided by 1, which is 1. 1 divided by 2, which is 1/2. 1 divided by 4, which is 1/4. 2 divided by 1 is 2. 2 divided by 2 is 1 again, so no need to write it again. 2 divided by 4 is 1/2 again. No need to write it again. Next, 3 divided by 1 is 3. 3 divided by 2 is 3/2. 3 divided by 4 is 3/4. And lastly, 6 divided by 1 is 6, because 6 divided by 2 is 3. 6 divided by 4 is 3/2. So therefore, what you can notice there is that we have 1, 2, 3, 4, 5, 6, 7, 8. 8 possible roots. But that's actually incorrect. We have 16, because again, we're considering both positive and negative. So the technique that I want you to understand here, class, is that when we're talking about factors and possible roots, they should be both positive and negative when you write them down. We're considering both sides, okay? So how do you maximize or use the concept of the rational root theorem in order to find the roots as indicated in the instructions? So the long method is basically applying the remainder or factor theorem by substituting all of the possible roots one by one. So if you do that, you're gonna have the following answers. You have those answers right there, and the goal here to identify what the root is that it should be the one that satisfies the equation. The meaning of that is we're going to take note of the ones that gave us 0. So we have negative 1/4, we have x is equal to 3, and lastly, we have x is equal to negative 2. So those 3 possible roots are our actual rational roots, because all of them gave us 0 when we substituted. That's the meaning of satisfying the equation, and that is the meaning of being a root or roots of a polynomial. So again, when you substitute them, it's gonna look like this. You have x is equal to negative 1/4, x is equal to negative 2, and x is equal to 3. Again, the meaning is that they are the roots of the polynomial. So later on, after this, we're gonna show you how to maximize the skills of your past in order to answer these kinds of questions. But the rational root theorem, again, the basic concept of it, the long version of it is you list down all the possible roots and then you substitute them one by one and find which ones will give you 0. Okay? So to continue with this one, let's say that we have now 2x cubed plus 11x squared plus 12x minus 9. So first that we do here is we identify our constant being negative 9. So we write negative 9 here. Then our leading coefficient being positive 2. So what I want you to understand here, class, is that when we're dealing with factors, immediately go with positive, negative. So the first one you can think of is always 1. So what number is it that you multiply to 1 to get 9? It's simply 9. Next, what other factors do we have for 9? It's just 3. It's 3 times 3 is 9. So you have 3 factors for the constant. Next, factors of the leading coefficient, you only have positive 1 times positive negative 2. So your possible roots are as follow. Sorry if my way of writing is not that good, but anyway. So we have 1 divided by 1, so we have positive negative 1. We have 1 divided by 2, so we have positive and negative 1 half. We have 3 divided by 1, so we have positive negative 3. 3 divided by 2, so we have positive negative 3 over 2. So we have positive negative 9, and lastly 9 over 2, so we have positive negative 9 over 2. So in here, we actually have 12 possible roots. Now, if you want to, I'm giving you this time to pause this video and substitute them one by one until you find which ones among those 12 possible roots will give us the 0 we're looking for. So, in this case, if you did the long version of it, you'll be able to get the following. 1 half, negative 3, and negative 3. Now, here's the thing that I would like for you to understand. You cannot get negative 3 twice when you substituted. Because if you substituted all of the possible roots listed earlier, you're only going to get 2 zeros in there. So why is that? So if we do this, this is how it works in order for it to not be as long as earlier. What you can do, once you get a 0, you use that to do synthetic division. So imagine the first root that I got, let's say x sub 1 is negative 3. Instead of finding the other 0 by substitution, what I'll do is synthetic division instead. So say I have negative 3, then I divide what? 2, 11, 12, negative 9. So continuing with this, 2 times negative 3, negative 6, 5, negative 15, negative 3, 9, 0. So I have here 2, 5, negative 3. So this means, you can follow, this is 2x squared plus 5x minus 3 equal to 0. Because again, there is no remainder. Now, this is the part that I was saying earlier. If you know the quadratic formula, you can get the other roots. Okay? You may do that. Now, if you don't know the quadratic formula, we can actually apply factoring. So that is the next thing that we can do here. We can apply factoring. So how does that work? So you can simply have two binomial factors. So 2x squared, the factors of that is simply 2x and x. And then negative 3, the factors of that is 3 and 1. And as you can observe in the middle part that we have here is positive 5. So we have to make sure that the sum will be positive 5 if you do FOIL method, right? So here, to make this thing quick, our answer here will be 2x minus 1 and x plus 3. Because negative 1 times 3, sorry, negative 1 times x is negative x, then 2x times 3 is 6x. Add those two things, you'll get 5x. So what you will do here to identify the other roots, after using the first one you got, which is negative 3, you will isolate each variable by equating them to 0. So you have 2x minus 1 equal to 0, x plus 3 equal to 0. So this will be x is equal to negative 3. This one will be 2x equal to 1, x is equal to 1 half. Hence our answers. Our roots are 1 half, negative 3, and negative 3. Okay, next. So if you don't want to do factoring, you may do continuous synthetic division if you also stumbled upon 1 half. Because again, what we're showing here is that you will not be able to see negative 3 and negative 3 twice when you do substitution. So what I will do is I will use 2, 5, negative 3 and we'll continue with it. Okay, so how does that work? Now we're going to use 1 half as our synthetic divisor. 2, 5, negative 3. Bring down 2. 2 times 1 half is 1. This will be 6. Times 1 half is 3. This is 0. So since this is 1 half, we divide this thing by 2. So what we're going to get is 1 and 3. Which means x plus 3 equal to 0. And again, we can isolate the variable. So x is equal to negative 3. So again, same answer, different solution. And again, you can also use the quadratic formula and you will have that kind of answer. So the purpose of this is, you can notice, if you do substitution like the first example, you are expected to have 3 different roots because it's a qubit polynomial. But in this case, the roots repeated. Negative 3 and negative 3 repeated. So how would you state your answer here? Your actual roots here, guys, is actually 1 half is your first, and negative 3 multiplicity of 2. So the meaning of multiplicity of 2 is simple. How many times did it repeat? 1, 2. Hence, 2. The negative 3 is your root. So you start by having the root multiplicity of the number of times it repeated. So we have 3 roots there. Now for you to understand this better, we can have our next example. X raised to 3 plus 12x squared plus 48x plus 64. So our constant here is positive 64. Our leading coefficient here is simple. It's 1. Because this is x raised to 3, guys. Kapag x raised to 3 yan, guys, it's automatic that there is a 1 next to it that we don't write, okay? So always 1. So factors of the leading coefficient is positive, negative 1. For the constant, positive, negative 1. We multiply that to positive, negative 64. What else? Positive, negative 2. So positive, negative 32. We also have 1. Positive, negative 4. Positive, negative 16. Also have positive, negative 8. We multiply that to 8 also. So we have those following factors for the constant. And since, as you can notice here, guys, I want you to understand this. I want your lives to be easier. If the factors of your leading coefficient is simply positive and negative 1, all you have to do is to copy and paste this. Whatever is your factors of constant, you just copy it. Since your factors of the leading coefficient is just 1. Okay? Again, if only it's 1, you can do this. Not all the time. Okay? It doesn't work all the time. So now again, what I said earlier, you can now start substituting all of them if you want to. But here's the trick. Here's the thing. Only one of them will give you 0. But again, you're expected to have 3 roots here. Now, disclaimer. In the examples that you're seeing right now, we're just dealing with rational roots because that's the focus of the lesson. But in some examples, you're not gonna be able to get the rational roots because sometimes given polynomials have irrational roots. So that's what I want you to remember. Now, if you do this, again, you can pause this part if you want to substitute all of them. Because there's going to be like what? 14 roots here. Now, if you're lucky, you'll be able to get the actual root being negative 4. So for us to verify that, let's again try out using synthetic division. So let's have negative 4. Then we have 1, 12, 48, 64. So we bring down 1. 1 times negative 4, negative 4. This is 8. 8 times negative 4 is negative 32. This is 16. This is negative 64. This is 0. So now what you can see here is 1, 8, 16. And we're still missing 2 roots. So what's the meaning of 1, 8, 16? This is x squared plus 8x plus 16 equal to 0. This is factorable. So we can identify the factors. So the factors, again, binomial, equal to 0. X squared, x times x lang yan. 16, 4 times 4, because 4 times 4 is also 16, and 4 plus 4 is 8. And since everything is positive, basic plus 4 lang yan. Equate to 0. X plus 4 equal to 0. X plus 4 equal to 0. And as you can notice, x is equal to negative 4. X is equal to negative 4. Imagine that. So as you can notice here, the one that we use synthetic divisor, the one that you can get by trial and error, substitution, remainder factor theorem. And when you do factoring, after doing synthetic, you can see that there's 3 negative 4s. So what are the roots of this polynomial? Simple. The roots are negative 4 multiplicity of 3 this time, because it repeated 1, 2, 3 times. So that's how it works. So I've shown you guys here 2 examples of multiplicity so that you can understand that even if you substitute all of them, there are cases that you might not be able to get the number of roots that you're looking for. Again, consider this. They can be irrational, imaginary, or in this case, it might be repetitive. That's why multiplicity. So let's go for some more examples right here. Let's say we have x raised to 3 minus 18x squared plus 108x minus 260. Now, disclaimer, the examples I'm showing are filled with multiplicity because it's the complicated part. But for some examples, it's just like the first one, walang multiplicity. So just list down the roots. Anyway, for this case, our constant is negative 216. My goodness, that's too high. Then, our leading coefficient is 1. So, positive, negative 1 ang factors natin for leading coefficient. Now, for 216, madami yan. We start with positive, negative 1. The technique here, guys, if the number is too high, what to do is start with the lowest number that is correct. So, 1. So, 216 divided by 1 is 216. Next, anong number next na mababa? After 1 is 2, because 216 is even. So, positive, negative 2. 216 divided by 2 is what? 108. So that's how it works. Next, is 3 possible? Yes, sir. So 216 divided by 3, we're gonna get positive, negative 72. After 3, what's next? We can do positive, negative 4. So 216 divided by 4, we have positive, negative 54. Is 5 possible? No, 6? 6, yes, sir. 6 is possible. So 216 divided by 6, you're gonna have positive, negative 36. Is 7 possible? No. Is 8 possible? Yes. So positive, negative 8. So divide that by 216 divided by 8, you're gonna have 227. And this can still continue. 10? No. 12. 12. Positive, negative 12. And you're gonna get 1, then 96. So that implies 96 divided by 12 is 8. Is it 8? No. 1. Yeah, it's 8. So 1, 8. 18. Are there other numbers that we can use here? None. So this many, right? And again, just like earlier, since this is just positive, negative 1, we'll just copy and paste our possible roots. So if you do this manually one by one, funny enough, as many as those are, you have 2, 4, 6, 8, 10, 12, 14 times 2, 28 possible roots. Only one of them will give you 0, and it's 6. So again, if we try this out, let's see if it's multiplicity. So let's do synthetic. We have 1, negative 18, 108, negative 216. Continuing, 1 times 6, 6, negative 12, negative 72, 36, times 6, 216, you get 0. So this means x squared minus 12x plus 36 equal to 0. This is also factorable. We have x minus 6 times x minus 6. Wait, the PDF is saving x minus 6 equal to 0. This is x minus 6 equal to 0, x minus 6 equal to 0, x is equal to 6, x is equal to 6. So again here, our roots repeated. This implies that our roots are as follow. 6 multiplicity of 3. Because it repeated 3 times. So it's multiplicity of 3. And finally, last example. Is it the last one? Okay, it's the last one. Finally, it's the last one. So we have here 36 as our constant. Leading coefficient natin, 1 lang ulit. Factors, positive negative 1, positive negative 36, positive negative 2, positive negative 18, positive and negative 3, positive and negative 12, positive negative 4, positive negative 9, positive negative 6. So for factors of LC, positive negative 1, copy and paste lang, same lang siya dito. So I'm so sorry if I'm doing it this way na, but on your end, you have to write them down one by one. And then if you substitute all of them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 18 possible roots, you're gonna get 4 roots. Okay? But again, that's the highest number of roots that you can get. That's at most. Not exactly. At most. Kasi nga, guys, may examples na pwede tayo magkaroon ng imaginary. Okay? So, in this case, we have negative 2, 2, negative 3, and 3. So again, as a tip, if you manage to get one of them, 2 of them, you may do synthetic division continuously. Now we're going to do synthetic division continuously in this case. So let's say we have negative 2 first. We have 1, 0, negative 13, 0, 36. The 0 stands for the x raised to 3 and the x raised to x. X. Because again, they're not here. So we have to have things for its place value. So 1, negative 2, negative 2, 4, negative 9, 18, 18, negative 36, 0. So we have here, again, you can do continuous here. So let's try 2 naman. Let's try 2 instead. So let's say 2. 1, negative 2, negative 9, negative 18. Bring down 1, 2, 0, 0. Wait. Oh, why is this negative? So sorry. Positive, supposedly. Okay. Negative 18, 0. This one right here is 1, 0, negative 9, meaning x squared minus 9 equal to 0. This is x plus 3. And x minus 3, a difference of 2 squares. Equate to 0, x plus 3 equal to 0, x minus 3 equal to 0. So this is x equal to negative 3, this is x equal to positive 3. So you manage to get your 4 roots. Now, I'm showing you the solution part here. If ever you got 1 or 2 roots, you can do this one already. But if you want to substitute all of them one by one, that's your choice. Okay? That's why we have the answers immediately here. And if you know how to use your calculator, it might lead you to these answers. But the purpose of the solution below is to verify if the roots are correct. So again, whatever roots you got first, if it's raised to 4, use 2 in order for you to get the others and do factoring. Now, here's the thing. If you want to do continuous synthetic division 3 times, there's no one stopping you. Like, you can still do synthetic division with 1, 0, -9 using any of the 2. And you will see you'll still get the same answers. That's how these kinds of concepts work. There are different kinds of solutions. Okay, so I hope you guys understood how remainder theorem, factor theorem, and the rational root theorem works. And that ends this video about remainder, factor, and rational root theorem. I think you guys are ready for your much awaited exams. That's why you're watching this probably, because we've already discussed this. Why are you here, right? This was already discussed to you. You're here to somewhat refresh your memories, and hopefully you were able to do that. And this part that nobody watches, I just want to say this one thing. A lot of things happened for the past few days, weeks, and I've had a lot of time to think about it, and sometimes it's the same thing with this whole account. Like, why do I do this thing? To be honest, I created this probably 2 or 3 years ago when the pandemic started, and it was my way to offer help to the students, whether those that are mine or those that are far. So that's why sometimes in general I forget that this might reach some other students, and yeah, I make it not just for my kids that are in the institution, but also for those who will stumble upon this one. At the same time, since nobody watches this part, I want to say that I actually want to make this grade 10 videos, because not only do I learn from it, learn on how to explain these ideas better, but at the same time, I want to make this as like a parting gift for my grade 8s last year. They're now in grade 9, so they will be in grade 10 next year. Because as much as I would like to be their teacher again, I really want to leave. I really want to leave. That's why I feel bad for the past few weeks, because I don't want to leave like that. That's why I still stayed, because I want to leave with the best possible year. And you know, now with everything that happened, I knew that it had to happen. Things have to get crazy at the end of it all. And we're just halfway through the journey, and I just thought I'm not gonna give up now. I've worked my, I've worked. I almost said something wrong there. I worked the best I can, overworking for all this thing, and I'm not expecting that it gets reciprocated immediately. It will make sense in the future. I know that. But my point is that I'm not gonna let those things that happened for the past few weeks define this academic year. Not just for me, but for the kids that are around me. I want this to be something that is filled with lessons and, of course, some chaos and fun. And that's what I realized, that maybe it's a matter of perspective. Now we have to remember where we started, what we have established, and go right back to it, but not basically starting over again, but learning from what has happened from day one to now, and start another day one where we are much better people around each other. Because at the end of it all, what I'm doing right here is a way for me to heal, and at the same time a way for me to reach out. um I've never had like a closure with my high school life, and it's because teachers took it personal when I did some mistakes. And that's why when I say something, whether it's in a calm manner, in a somewhat louder manner, I always make it to a point that I want the students to understand that I've been in their shoes, and they have to hear it. And the best person to tell it to them is me. And I'm taking that. I know, wow, why is Mr. Alcantara, or the great teacher, saying that it has to come from him? I just think that If they're not gonna hear it from others first, it has to come from me. No matter how bad I said it. I admit it. I there's some words that I wish I could have worded out properly, but I realized I cannot take it back now. Instead, I'm gonna live by it. Not to continue with it, but instead to make people understand that we all make mistakes and we should not be defined by those things. Those things that has to come from me, they are not entirely true, they're partially true. That's what I have to go with it. Because people need to understand that once we get out of this zone, this classroom, these four walls, we are different people. And these four walls that I'm in, I'm not necessarily the great teacher here. I'm everything here. This small space that I've been living in for the past 10 years has defined me as someone who won't let things die, because I want to give my best in order to reach out, in order to help out. And I'm gonna fail. I'm gonna fail a lot of times. Your teachers are not perfect. We're humans. We're never gonna be perfect. But I want to give my best to be the perfect teacher to write this story with you guys. And I don't know if that's gonna be possible, but we'll try. At least we'll try, right? Right, Coco? Coco's looking at the camera because it's been too long. Nobody watched this part anyway, but all I can say is that is all I can say. I had to do those things because to finish this off right, it's been long already. It's not part of the lessons, but a values integration for Christmas sake, Merry Christmas. One of our students asked this question: what motivates you to wake up in the morning? What helps you continue living, and some sort of that. I asked him again personally if he could talk to me about that question. I didn't answer it in front of him, but I want to answer it now. I cannot expose myself way too much anymore about who I am behind the camera, behind the stage of our four walls in our classroom. But here's the thing: 2023 is the worst year for me. Not because of things and blah blah blah. This something happened. I hope I know some of people. When you lost someone, it's gonna be the worst. But since I've managed to be in this predicament where I've learned a lot in managing my emotions, I have learned to control them, to hide them for the meantime, some sort of things. I've learned to live through it. And you guys, my students, former students, and even those who I don't know that will stumble upon this, were the ones that I look forward to seeing in the morning. That's why I'm making this video 12 a.m. and I have work tomorrow later, and I have a lot of things to do, but I'm still making this one because I look forward to see you guys. And I don't want to say that much because that might go all over their heads, but you know what? I just have to say that. And I look forward to the end of the school year. Not only because I want to try something new with my life, but at the same time, I want to see how great we did, you know? Because at the end of the day, the great teacher is not just me, it's all the memories we've made along the way. And that's it for this memory. This is a long one, 8 minutes for an outro, right? But anyway, soon enough, in 6 months, in case you won't see me, hope you don't see me. I'm just kidding. I need to hide. Good morning, good afternoon, good evening, and good night. Peace out, everyone. Respect.